The next result we want to discuss about the exponential map is the following theorem, which says that the exponential function maps the complex plane onto the plane minus 0, and it does this in kind of an infinity to 1 manner. More specifically, any non-zero complex number can be written as exp of z for z in the complex plane, and this is unique up to translation by 2 pi I times the integers. So w will also be the exponential of z plus 2 pi I times an integer, and these are the only inverse images of w under the exponential map. Let's see why this is true. So the hardest part is the onto aspect, given what we've already proven. So let's look at the proof. Let's first try to solve for the correct z that does what we want. So we're given w and we're trying to find a z so that exp of z equals w. Can we do it? So the first thing to look at is that if we had a z, then modulus of w would equal exp of the real part of z. And so the first thing is we can figure out what the real part of z is. E to the x, where x is real, increases from 0 to infinity, and so it attains every positive real value. In particular, we can attain modulus of w, so we declare x to be the unique real number such that e to the x gives you the modulus of w, and so that pins down the real part of the z we're looking for. Now we have to find the imaginary part. Okay, and the way we do that is we need to solve e to the iy equals w over modulus of w. So we're going to choose a y so that cosine of y, again the real part of e to the iy, gives me the real part of w over the modulus of w. Now this real part has to be between -1 and 1, and cosine of y is perfectly continuous in everything, and it attains the values 1 and -1, so we can certainly fit this requirement. And I'm not saying this that this y does what we want yet. There's a couple possibilities. So what we get out of this is that sine of y will be plus or minus what we want, just because we'll automatically have that sine squared y will be the imaginary part of w over modulus of w squared. So we get the right thing up to a plus or minus. So from this, we would get that exp of iy is either the thing we want, w over its modulus, or x of negative iy gives us the right thing. But in either case, we'll get, in one of these cases, we'll get what we want. So exponential of either x plus iy or x minus iy will give us w. And so then the uniqueness so that solves the part of constructing one inverse image. And then the uniqueness aspect follows from what we already proved, that exponential of z equals 1 if and only if z is 2 pi I times an integer, because if I have one inverse image, say z naught, exp of z naught gives me w, and I already found a different one, well, then we have exp of z minus z naught is 1, so this difference has to be 2 pi I times an integer, and then as we already kind of remarked, if I add 2 pi I times an integer to a given preimage, it still gives me a preimage. So this proves the main statement. One of the things we get out of this is the polar decomposition, which I've written it kind of in an exponential form. If I have a non-zero complex number, I can always write it as e to the x. So usually you'd write this as r, but it's just a positive number, times e to the iy, and again, y is unique up to 2 pi z in this case. Now, because of the feature that two complex numbers will map to the same thing under the exponential map if they differ by a multiple of 2 pi I, so if we restrict the exponential map to a domain where two numbers cannot differ by 2 pi I, so here what we've done is the valid x's are all real numbers, but then the y's that we allow are just in an interval of length 2 pi. So because of this, exponential map restricted to such a set will be 1-to-1, and it'll be onto because we can always pick a representative of an inverse image from this set by translating until we get its imaginary part in this interval, which we can always do. And so then we see that exponential will map a strip like this from where y goes from a to a plus 2 pi. So that's what this set is. It's a strip. It maps it to the whole plane minus a point. And here I've drawn in where some other things go. If I have a horizontal line, so that's where y is fixed and x is allowed to vary. Well, if I have y fixed and x is allowed to vary, we really just get a ray because we have a specific complex number and we're just taking multiples of it. So we'll get some ray, and where it's at basically depends on the angle or the value y. On the other hand, if I look at a vertical line, which I've drawn in blue, this is where I have x fixed, and that means we're at a fixed radius, and we have to hit all points with that radius, so we parameterize the entire unit circle with a vertical line right here. And then if you went and extended this and looked at the exponential map on the entire plane, you'd see that it maps each one of these strips in the same way. So each strip gets mapped in the same way onto this picture. And so that is another way of seeing that you have sort of the exponential map on all of C is infinite to 1. So one thing I just mentioned up there is that we can use the exponential function that we built to parameterize the circle of radius r. So gamma of t equal to r e to the it, where t goes from 0 to 2 pi. This will give you a parameterization of the circle of radius r. And again, you get it from the argument we've given that we'll hit every point on the circle of radius r through the exponential map, and the only points that we hit twice would be at 0 and 2 pi. And that's how you sort of wrap around the whole circle. And you can take the derivative of this and it'll give you the tangent vector of this parameterization, and this is sort of a particularly important parameterization because it has a fixed speed, because if I take the modulus of the derivative of this, so the derivative was IR e to the IT, and its modulus will just be R, so it's constant speed parameterization of the unit circle.